All right, good morning, everyone. I was all scared I was going to be here by myself and I have to talk to myself for an hour and 15 minutes. So that'll be fun. So welcome to our last class. So tomorrow, again, is the exam, but Jolie already knows she doesn't have to take it tomorrow, so that's fine. So anyways, feel free to ask questions. I'll let Tara catch up. So today we're going to finish off. We only got a couple more things to talk about, and then we'll be finally done. So let me share my screen here. So first thing I want to talk about is combinations of lenses or combinations of lenses and mirrors. So basically the importance of this is that pretty much almost all optical instruments, at least useful optical instruments, are made up from combinations of lenses or combinations of lenses and mirrors. You could have many, many different options. So a couple examples of this would be telescopes. So typically if you're bought a telescope, you know, a place like Walmart or on Amazon or something, you usually get one of two different types. So one is what's known as a refracting telescope. That's one that deals with two lenses. Or there's one which is known as a reflecting telescope. So that one is a lens and a mirror, or you can have other possible combinations. So that's one particular example. Microscopes are usually two combinations of two lenses, periscopes, combination of lenses, and etc. So here we can have all kinds of different possibilities, but let's consider a scenario down here. So here we want to know what is the image formation and magnification of the image which was created by, say, two, in this case, converging lenses, which are separated by some distance d. Kelly. So let's say these guys are separated by a distance of d. So this is my distance d between the two. Good. So I know you already saw this in lab, but let's go ahead and formally kind of talk about it. So let's say I put a object here. So here's my object, and I want to know, where does this thing actually show up? Well, let's first talk about our ray diagram. So the way that we do ray diagrams is we're pretty much going to draw a ray diagram for the first lens, ignoring the fact that the second lens even exists. So we're not even going to touch the second lens. Once we create the image from that first lens, that image from the first lens becomes the object for the second lens, and now we're going to use that to draw the ray diagram for the second lens, ignoring the fact that the first lens even exists. Okay? So what do I mean by that? So what I mean is we're going to draw our usual two rays. So I'm going to start off with ray number 1, which is going to go parallel to the principal, go to the center of the first lens, and then get refracted through the focal point. Kind of missed that focal point, but that's okay. Close enough, I'll move it. There we go. There we go, put our focal point there, just because I missed it. And then let's draw our second ray. So the second ray then is going to be the one that goes through the closer focal point. There we go, through here. Hit the second, or arrows in, if I could speak, middle of the lens, and then gets refracted parallel to the principal. So it goes off in this direction. So great. And again, where these guys intersect with each other, this is now going to give us our first image. Okay? So this is now our image. Now this image, even though it's the image from the first, this image now becomes the object for the second lens. So for the second lens, now we're going to ignore the fact that the first lens actually exists, and now we're going to redraw our ray diagram, but now using this as our object. So here, this is what we're going to call object number 2. So here again, we're going to draw ray number 1. So it's going to go through the center of the second lens, get refracted through the focal point of the second lens. So this is ray number 1 for the second object. And then ray number 2, again, it's now going to go through the focal point on the near side of the second lens, at the center of the second lens, and then get refracted through the lens, so that is parallel to the principal. Where this guy intersects this one, so where these two rays intersect with each other, this is then the location of the final image. So this is how we draw our ray diagrams. So for the ray diagrams for multiple lenses, we just draw a ray diagram for each individual lens, ignoring the fact that the other lens actually even exists. So even if I had a third lens out here, I would do the same thing. So for the third lens, I would use this as now the new object, and then draw that image from that for that new object, and then etc. So even if I had 150 different lenses, I would do exactly the same thing. So good. So here, let's get our nomenclature. So this distance here, we're going to go ahead and call our our object distance 1. This distance here is what we're going to call then image distance 1. This distance here then is what we're going to call object distance 2. And then this distance here is what we're going to call image distance 2. So our final image is equal to image distance 2. Okay. Now, typically the way this is going to work is our eye is over here, which is looking at the formation of this image. Okay. So typically we're going to look at where is this guy created from this second lens. Okay. So this is the location of our eye. So mathematically, the way this is going to work is we're simply going to use the lens equation and the mirror equation separately for each one of these different scenarios here. Okay? So which this means is that for lens 1, which has focal length FA, we're simply going to say, okay, so 1 over then the object distance 1 plus 1 over the image distance 1 is then equal to 1 over the focal length from lens A. So from here, as long as this is a converging lens, we would then find that the image distance 1 is then going to be equal to the object distance 1 times the focal length of A divided by object distance 1 minus focal length of A. Now, to determine now object distance 2, notice that image distance 1 plus object distance 2 is equal to the separation distance between the two lenses. So we can then say the separation between the two lenses is equal to image distance 1 plus object distance 2, which means that object distance 2 is then going to be equal to the separation distance minus image distance 1. Now that we have object distance 2, we would then use again our lens equation or mirror equation, if this happened to be a mirror, to then determine what is the final image distance. So we say that object distance 2 plus 1 over image distance 2 has to then be equal to 1 over the focal length B. So in this case, it's the focal length of this particular lens, which is FB. So finally, our image distance 2 then would be equal to the object distance 2 times focal length B divided by object distance 2 minus focal length of B. Now again, be a little careful here what we wrote down. This is only true for a converging lens. This is also only true for a converging lens. I don't think these are always that. But this statement here, which I'm going to write in red, this is always true, regardless of the type of lenses that we're using. So this is always true. So this is how we would then determine the final image location. So the final image location, DI2, then would be solved this way, which would be the distance away from this second lens. Okay. Now the magnification would then simply be equal to, so here we would find the magnification. So here we would have two separate magnifications. We would have magnification MA, which then would be equal to minus image distance 1 divided by object distance 1. And this is magnification from lens A. And then we'd have magnification B, which would be magnification from lens B, which then would be equal to minus image distance 2 divided by object distance 2. So the total magnification is actually just the product of these two magnifications. So the total magnification, I'm going to call M total, is then equal to MA times then MB. So it's going to be equal to simply image distance 1 times image distance 2 divided by object distance 1 times object distance 2. So this is our total magnification. Now, if I had more than 2 lenses, for example, then I would simply multiply by the magnification of the next lens. So if I had 3 lenses, for example, then I would have MA, MA, or MB, and then MC. So I would just have the product of all of them. So for more than 2 lenses, then the total magnification would then be equal to the product all of those magnifications. You guys ever seen this before? A capital pi with an I underneath of it. So capital pi with an I is equivalent to a sum, or sigma with an I. So this means that this is a sum. This is what's called a product. So it just means I'm going to multiply all these guys out. So this would be the same thing as what? MA times MB times MC times blah, blah, blah. Okay. So it's just a product over all of them. Yeah, they don't ever teach the infinite product. They always teach the infinite sum and never the infinite product. Never know why. Anyways, my own personal thoughts. So let's use this and consider an example. Okay. So this example says we have, no, that's your workshop. Never mind. Here we go. We have two converging lenses, A and B, which A has a focal length of 20 centimeters and B has a focal length of 25 centimeters, and these guys are 80 centimeters apart. So it says an object then is placed a distance 60 centimeters in front of the first lens. So it wants us then to determine the position and the magnification of the final image formed by this combination of lenses. Okay. So let's write down everything we know. So we know that FA is going to be equal to 20 centimeters. We know FB is equal to 25 centimeters. We know that object distance 1 is then equal to 80, and then D is equal to 60. So this is equal to 80 centimeters, and D then is equal to 60 centimeters. So from here, since this is two converging lenses, we can just actually write down everything we just did. So we know that image distance 1 is then equal to object distance 1 times focal length of A divided by object distance 1 minus focal length of A. So this is then going to be equal to what? So it's going to be equal to 80 times 20 divided by 60, right? Okay. So this 0 is going to cancel with this one. So this is going to become a 4/3. So this is going to become 4/3 times 20, which is then going to be what? 80 divided by 3. So 80 divided by 3 centimeters. I'll write it that way. Okay. Object distance 2 then is going to be the same thing then as D minus image distance 1. So in this case, this is going to be the same thing as what? 60. So that's going to be 120 over 3 minus 80 over 3, which is going to be the same thing as, if I can do bad math in my head, 40 over 3. Okay. So this is going to be the new object distance. And then finally, our final image distance. So image distance 2 then is going to be object distance 2 times focal length of B divided by object distance 2 minus focal length of B. So this is going to be equal to 40 over 3 times 25 divided by, so 40 over 3 minus 25. So 25 by 3, that's 75, right? Yeah. So plug in our numbers, we find in this case then is, that should be 50, if I did my multiplications all right. Good, so it should be equal to 50 centimeters, okay. So where did I go wrong? So I got 80 times 20, good, divided by 60, 80 thirds, okay. Good. Okay, good, so that's all fine. So the total magnification, so that's all part A. So part B, the total magnification then is going to be equal to, again, the image distance 1 times image distance 2 divided by object distance 1 times object distance 2. So it's going to be image distance 1, so that's 80, divided by 80 over 3, times then 40 over 3 divided by 50. Okay. So the 80s are going to cancel, the thirds are going to cancel, So in this case, this should be equal to, if I did my math properly, according to what I did before, this should be equal to a half. Still puzzled by that. Okay, it was okay. So basically the only differences would be what? So if I went back to my previous pages here, this would be different than if I had a diverging lens instead of a converging lens. The only thing that would be different would be the focal length would have to be negative. But everything would be the same if I had a mirror instead of a lens. The only difference is now I just have to know if it was concave or convex. But nothing too bad. So good. So the last thing to talk about is what happens when I have different shapes of lenses. So for example, what we considered were lenses that kind of look like this, but we don't necessarily have to have that. We can have a lens that does something like this. I could have a lens that does something like this. I can have a lens that does something like this. It's supposed to be a straight line. There we go. I can have all kinds of different possible different configurations of radii and how all these things are actually aligned with each other. So the question is, if I have something like this, which has all kinds of different possible shapes to the lens, then what is the focal length of the lens? So this is what brings us to what's known as the Lensmaker's equation. So what the Lensmaker equation says is how to determine the focal length for a lens that has different type of radii. So let's draw an example. So let's say this side here looks something like that. Let's extend that over to here. And I'm going to draw a smaller radius on this side. So let's say I have a lens that does something like this. So this left lens here has a particular radius. This radius we're going to draw here. So this has a radius does something like that. I'm going to call this radius R1. So R1 corresponds to the lens portion on the left-hand side. R2 then is going to correspond to the radius of the lens portion on the right-hand side. So this is R2. So what the Lensmaker equation says is that 1 over the focal length is then equal to the index of refraction of the material. So in this case, whatever this material for the lens is made out of has an index of refraction, n, minus the 1 times then 1 over radius R1 plus 1 over radius of R2. So the Lensmaker equation tells me then if I know the index of refraction of the material, and I know the radius R1 here, and I know the radius R2, then I can determine then the focal length. Now, things to pay attention to here are the radii are defined in such a way that, again, if the left side here has a radius which stems from the right-hand side, this is considered a positive radius. Okay. So the radius of the left lens here, on the left side of the lens, if that stems from the right-hand side, then that's a positive radius. The radius of the right-hand side of the lens, if that stems from the left-hand side, that is also a positive radius. Okay. So, for example, what does that mean? So that means for this first lens I drew, this is positive, this is positive. But for the second lens I drew here, the left-hand side looks like this, so that's positive, but the right-hand side is actually going to be negative. So this would be a negative radius, because it's on the same side as which R1 is, which is the opposite side of what it's supposed to be. For the next lens I drew, this one on the left-hand side comes from the wrong side, so this is actually negative, and the one on the right-hand side is also from the wrong side, so that's also a negative. It's supposed to be green. So this would have a negative radii, negative radii. For the one next to it, this would also be a negative radius, and then on the right-hand side, this radius would be infinity, right? Because it's a flat portion, which means it has an infinite radius. So we just simply call that guy infinite. Okay. So good. So the way I would know if this is positive or negative is I'd have to look at the lens and see, okay, is the left portion coming from something on the right-hand side? If that answer is yes, then that's positive. Is the right portion coming from something on the left-hand side? If the answer to that is yes, again, that's going to be positive. Anything else would then be negative. Now, once I use the Lensmaker equation then to determine the focal length, I would then just proceed through the problem as if I now know what the focal length is and I don't have to worry about anything else after that. So for example, let's do an example. So this example says that we have a convex meniscus lens, is a convex lens on the left-hand side, and a concave lens on the right-hand side. So it wants to know if the lens is made out of a glass, which has a an index of refraction of 1.5, radius of curvature on the left, which is 22.4. On the right-hand side, that is then 46.2, determine the focal length. And then after that, we want to know where will the image be formed if an object is sitting 2 meters away. So basically, the Lensmaker equation is going to give me the focal length. Once I know that focal length, I just proceed through it using the usual lens equation that we had before, so the thin lens equation. So once I know that, then everything else I just treat as if the same thing. So good. So let's draw this scenario. So this is telling me that on the left-hand side, this thing is convex. So remember, convex bends outward. So this is convex on this side. But on the right-hand side, this thing is concave, which means we go into the cave, so it actually looks something like this. So this is our lens. Now, what it's telling me then is that the radius on the right-hand side, R1, was equal to what? 22.4 centimeters. And then the radius for the right-hand side, which is then this one, R2, was equal to 46 point something. Where am I? Right here. 46.2. 46.2 centimeters. So what this means then is that R1, when we use our Lensmaker equation, this one is positive, but R2 is actually going to be negative because it's going on the wrong side. Okay. So that means when I write out my Lensmaker equation for part A, this tells me that 1 over the focal length then is equal to the index of refraction minus 1 times 1 over R1, but R1 is positive, R2 is negative, so I'm going to go ahead and write this as negative R2. That way I'm going to use it as the magnitude of simply this guy. So good. So this tells me that I have 1 over f then is equal to 1.5, because that's n, minus 1, times then 1 over 22.4 minus 1 over 46.2. Then when I invert that, this gives me then that the focal length then is equal to 87 centimeters. Okay? Now, since the focal length then is positive, is that a converging lens or diverging lens? So if the focal length is positive, is that converging or diverging?
Would it be converging?
Very good, that's right, it's a converging lens. So here, we now just have simply a converging lens. So when I go to do my ray diagram, because I like drawing ray diagrams, we're just going to treat it as a converging lens. Okay. So let's get a little more practice. Let's draw a ray diagram for this. So here we know that the focal length is 87 centimeters. So let's call this our focal point here. And then this has a equivalent focal point on this side. So it's a little closer over here. There we go. And we know that we're going to put an object 2 meters in front of that. So if this is about 100 and then another 100 is about here, so my object should be somewhere out here, right? So it's going to be about 2 meters. So in this case, I know my object distance is equal to 2 meters. Good, so let's draw a ray diagram. So again, we're going to draw ray number 1. Ray number 1 is the ray that goes parallel to the principal, hits the center of the lens and gets refracted through the focal point. So that's that one. Ray number 2 is going to go through the focal point on the near side. Almost missed that. There we go. To the center, and then gets refracted outward, parallel to the principal, so that the place where these guys meet up is the location of the image. Okay. So this is our image. So good. So here we should see that our image should be at a distance slightly bigger than that of the focal point. So something greater than 87 centimeters. So good. So let's find out. So here, since this is converging, what we know then is that the image distance is then going to be equal to the object distance times the focal length divided by the object distance minus the focal length. So it's going to be simply equal to 2 meters times 0.87 meters divided by 2 minus 0.87. This all has units of meters. Let me just get rid of that meters there. Plug in our numbers. Find in this case then is that this should be at 1.54 meters, which indeed is bigger than 87. So this is our image distance. That's it. So again, so the Lensmaker equation allows me ways to find out what exactly the focal length is. But as far as the calculation is concerned, once I know what the focal length is, then all I have to do then is proceed through the problem as if it's that type of lens. Okay. So here we found it's a converging lens, so I just treat it as a converging lens, and I just use that focal length for the rest of the time. And that's it. We're all done. Yay. So good. So let's do a quick review. So first thing we did was what? Chapter 22. So chapter 22 is mostly the behavior of light. So here we saw that the speed of light is equal to 1 over the square root of mu naught times epsilon naught, which is roughly about 3 times 10 to the 8th meters per second. And it's also equal to the amplitude of the electric field divided by the amplitude of the magnetic field, which is also equal to the RMS value of the electric field divided by the RMS value of the magnetic field. So this is then the speed of light. And again, this is only true in vacuum. If it's not in vacuum, then it moves at a slightly different rate. There we go. Depending on the index of refraction, but that was the next portion. So other than that, we also saw what? Our pointing vector. So our pointing vector S was equal to the electric field crossed by the magnetic field divided by mu naught, which means that our magnitude of our pointing vector, which is equal to the intensity, is equal to the electric field times the magnetic field divided by mu naught. Okay. Now, most of the time, we're going to write this then as the RMS value of the electric field times the RMS value of the magnetic field divided by mu naught, which is also equal to the amplitude of the electric field times the amplitude of the magnetic field divided by twice of mu naught. Right? So these two come from the average of this guy. Okay, so this is what it looks like all the time, but this guy comes from the averages. So these are from the average. And this is when it's oscillating very, very rapidly. So average of S vector. Okay. Good. What else? So from here, we then saw that what? We had radiation pressure. So P rad. So radiation pressure was the same thing as A times I divided by C, where A is some number between 1 and 2. So it is 1 when this guy is totally absorbing, and it's 2 when this guy is completely reflecting. Which also brings up the radiation force, which is then simply equal to the cross-sectional area. So this is cross-sectional area times radiation pressure. So it's going to be A times capital A times I divided by C. I think that's about as much as we did in that chapter, right? I think there was much more to that. All right, so now we can go to chapter 23. Would you stop doing that? Thank you. So chapter 23. So chapter 23, we now saw what? What do we see? What do we do first? Mirrors. So we did all the mirror equation, which is actually the same thing as the thin lens equation, which says what? 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. We saw magnification. as well as lateral magnification, but that's also the same thing. So we have the magnification is equal to the image height divided by the object height, which is equal to negative of the image distance divided by the object distance. So that's the magnification. We saw index refraction. Index refraction is defined as the speed of light divided by the speed at which it moves within the dielectric. So c is the speed of light again. V is the speed within dielectric. From here, we saw law of refraction, also known as Snell's law. So Snell's law says that if I go from one medium into another, where this is N1 and this is N2, then N1 times sine of theta 1 must then be equal to N2 times sine of theta 2, where the two angles are in reference to the normal line. So if I have 90 degree here and 90 degrees here, then my incoming wave, which is at an angle of theta 1 relative to the normal, and then this guy is refracted. So my refracted is going in this direction. This is at an angle of theta 2 relative to that normal on the opposite side. So this is Snell's law. And then finally, we just saw the Lensmaker equation. The Lensmaker's equation. And that says 1 over the focal length is equal to the index refraction minus 1 times 1 over R1 plus 1 over R2, where, again, these guys are defined this way, where this is R1 and this is R2. So again, if it looks like this, then this is positive, and this one is also positive. If it doesn't look like this, then make them negative. And that's it. And like I said, so basically combinations of lenses or mirrors pretty much works out exactly the same way. You just use the mirror equation or the lens equation for each individual object. Using that again, the new object distance is the difference. So object distance 2, for example, would be equal to the distance between the lenses minus image distance 1. And then again, the total magnification is just equal to the product of all the magnification. So M1 and 2 times M3 times blah, blah, blah. So good. So next thing we'll talk about is, so what to expect on the exam for those who are still planning on taking it. So there'll definitely be one question which deals with combinations of lenses mixed with Lensmaker's equation. So this would be, say, long problem number 1. So things to expect in here are things like, what's the final location of the image? Is it real / virtual? Is it inverted? Upright? And then here you have to give some sort of justification for these two. So usually going to be a why type question associated with that. So this will be justification. Okay, so this will be long problem number 1. Something dealing with all that. Long problem number 2 then would be dealing with mostly this stuff. So basically all of this stuff here. So this will be long problem number 2. So this is going to deal something with radiation pressure, with radiation forces, finding RMS values of electric fields and things like that from intensities, calculating intensities. So one thing you will also need for this question is remember that intensity is equal to power divided by area. Okay. Now, depending on what type of thing you're looking at, this area here will either be a surface area or it'll be a cross-sectional area. It just depends on what exactly the question is asking. So it's going to be a surface area if it's asking or it says that you have a point source. So this would be a point source or an isotropic source. In that case, then you would have to use the surface area of a sphere, which means that this would be equal to 4 pi r squared. Cross-sectional area, this would be something like if you're dealing with something more like a laser, something that's well confined, so it's not a point source. So in that case, the area would be the cross-sectional area, which would be pi r squared. So good. Good. So yeah, so the second law problem will be dealing with, like I said, basically intensities and RMS values and radiation pressure and all that stuff. Actually, I should include this up here too, since the relationship between these two is given by C. So should probably include all that in there too. Short answer questions will be basically a mixed bag of different stuff. So one thing to expect for short ones is dealing with either the mirror equation or the lens equation with just one lens or one mirror. Okay. So one particular short would be using this and say this with one lens or mirror. So not a combination, but just one object. Another one would be definitely Snell's law. Okay, so Snell's law. Oh, and there was one more thing we've got to write down, which is the law of reflections. So remember, the law of reflection says that the angle of incidence is equal to the angle of reflections. So here, if I had another portion which was reflected, so outward in this direction, theta r, then theta 1 is equal to theta r. So the angle of incidence is equal to theta of reflection. So that would be part of, say, the Snell's law problem as well. So that gives you at least 2. Third one, I think, actually does involve this guy. So one would involve this guy. Another one actually involves radiation pressure. So this will be another short answer one. So it's kind of a mixture of different types of stuff, but not too bad. So, any questions on any of these types of things? I think so. No. Okay. So good. So the last thing, keep you guys a little bit busy, are group assignments. So I have some more exciting group assignments for you. So let's talk about them. So the first one, let's talk about this one first. This is Snell's law problem. So this says we have a light beam strikes a 2 centimeter thick piece of plastic, which has a reflective index. So that's our index of refraction of 1.62. And it strikes it at an angle of 45 degrees relative to the incidence, or to the normal line here. So this is our plastic, index of refraction, and 1 is 1.62. And this angle here is 45 degrees. So what's going to happen here is it's going to get refracted. That refracted light is going to come down and then strike a 3 centimeter thick piece of glass, which in this case, we're going to take the index of refraction of the glass as 1.47. So at this portion here, it's going to come in, it's going to get refracted. So this has 1.47. That refracted ray is going to keep going down, and then it's going to refract through the glass and then go in the same direction as which this incoming piece is going. Okay. So what you want to know then is, what is the distance from where the light first goes into the plastic and then comes out through the glass? So what is this total distance of D here? So what I would say is, to do this problem, Figure out what this angle is here. Since you know this side length here, you know what this angle is here. You're going to use tangent and then to figure out this distance. So use Snell's law across this boundary. Then use Snell's law across this boundary here. And again, to determine what this angle is, once you know this angle and you know this distance, you can find this distance. So you're going to find distance D1 here and then distance D2, and then the total distance is just the sum of those two distances. So just do some geometry with applying Snell's law twice. That's all we care about here. So good. So that's that one. So that's the first one. The second one then says we have a lighted candle. So this is our candle out here. Which is 36 centimeters in front of this first converging lens, which has a focal length f1 of 13 centimeters. And then lens 1 is 56 centimeters in front of lens 2, which has a focal length of 16 centimeters. So you want to draw a radii diagram and then figure out what is the position of the final image away from the second lens, and then what is the size. Actually, I didn't tell you the size. So let's find the magnification. So what is the magnification of the final image? So change that to magnification. Magnification. There we go. I'll take that later. Good. So that's the second one. And then finally, the third one deals with the Lensmaker's equation. So this says we have an insect, which is 3.75 meters or millimeters tall, is placed 22 centimeters to the left of a thin plano-convex lens. So the left-hand side is flat, meaning that the radius of curvature is infinite. And then the right-hand side of it has a radius of curvature of 13 centimeters and an index refraction of 1.7. So it wants to know what is the location and size of the image the lens forms of the insect, and then is that real or is it virtual, and is it upright or inverted? So here, your first thing to do is use the fact that the radius R1 is equal to infinity, R2 is equal to 13. Use that then to determine the focal length using the Lensmaker's equation. Once you have the focal length, then you can just use the thin lens equation to then determine the location, and then use magnification to determine the size, and then from there you'll be able to determine if it is real or virtual and inverted or upright. So that's about it. So just 3 more to go. Not too bad. Not too bad. So good. You got about a half hour kind of complete all those. So I'll let you guys work on those. And then Shaylin, you can just hang out afterward, and then we can talk about what you want to talk about. Okay. Sounds good. All right, so let me split you guys up. So good. We'll do 2 rooms, 3 people in each room. Sounds good. Create those, open all rooms.
45 seconds by myself, and I was like, am I going to be by myself this whole time?
Molly, right?
It's going to be weird.
Yeah, sorry. I was like in between something working, so.
Hello, ladies. How we doing?
Hello. We got to talking, so we haven't actually started yet. We're all trying to decide if we're going to take the exam tomorrow.
Oh, gotcha. Well, you can ask me that after we're all done if you want. I'll put everybody into a breakout room by themselves, and then you can ask
You're
questions about
bleeding. I was like, yeah, I know. Why don't you help me catch her? Oh, she got bleeding? Took jetted after that.
that. Yeah, I basically ignored my family yesterday and reading all day, so it was fun.
Yeah.
It was fine. Okay, I'll be back.
Okay.
Hello, ladies. How we doing?
I think okay. The first angle, is it 25.9
It sounds about right.
for N1?
Yeah, because it's going from a low NX refraction to a high NX refraction, so yeah, it should bend towards the normal. Yeah, so it should be less than 45. Yeah.
Okay.
Here I can do that calculation real quick. Yeah, because in this case, N, it's going from N is equal to 1. Yeah. Yeah, because it's going from air, so. Sine of, that's not what I wanted.
For my N2, I got an angle of 28.751. I don't know if you guys have gotten there yet or not, but
I'm doing it right now.
Which angle was that for?
when you find your sine of theta 2, you do 1 over 1.47 times the square root of 2, and then you get 0.481, and if you take the inverse sine of that number, you should get 28.751, which I don't know if that's right, but that's what I
Yeah, so
got.
the
Yeah,
first
I got
angle,
28.8.
yeah, so the first angle
Okay.
should be 25.8977777, something like that. Good. Yeah, so let me check the next one.
28.6 for the third one, I think.
Okay. 1.62 times sine of 1.47. So it should be larger than the other one. Yeah.
Yeah.
W. W. Almost there. 0.5.
It's a long calculation.
Yeah, so 28.75-ish. Yeah, somewhere around there.
Okay, great.
So yeah, so now that you know those angles, then you can just draw two triangles, and then from those two triangles, you're just looking for the opposite side. So you can use tangent for both of those. Yeah.
So we would use our thickness and do 2 times the tangent of 25.913,
Correct.
and then plus the 3 times tangent of 28.751.
Correct. That's right. Good job. I'll be back.
Everybody's mad. Everybody's mad. Because we had like nothing due the first week, and then we have 2 papers and 3 labs due this week, and the final exam tomorrow. Everybody's mad.
What class is this for?
Exercise science 484,
Okay.
which was like summer, it started summer 3, so it's a 4-week course.
Okay.
And we didn't, like, he didn't do anything the first week. I was getting so nervous. and then like everything's due this week, and it's making so many people mad. So my phone is just over here vibrating like crazy because all the girls that I'm in a group chat with are having a fit.
Gotcha. I would ask you who's teaching it, but I don't want to post it all over YouTube, so don't answer that question.
I have a silly math question.
What's that? Oh, silly math question. Yes.
So when I'm just trying to solve for this initial theta 2.
Yep.
So like solving for the, yeah. So I have sine of 45 over n of the index of fraction of plastic.
Yep.
And then how do I get just the angle and not with sine with it? If that makes sense.
So take an arc sine of all of that. So take an inverse sine of everything. So ultimately, you're going to do inverse sine of sine of 45 divided by 1.47, or no, 1.62. Sorry.
Okay.
Yeah. So you should get an angle around 25.9 degrees, somewhere around there.
Mm-hmm.
All right, I did. Good.
All right. So now we're using that to find the distance. So.
Right. So now you want to set up a triangle and use tangent to find the distance of the opposite side. Correct.
Use tangent.
I just was so caught up in finding the angle. I'm like, boom, found the angle, I'm done. And then I looked at it again. I'm like, nope. I'm like, this is how I make mistakes on the exam. I get so caught up in finding something on the way to the thing that I find that thing and I'm like, I'm done.
That's right.
And then it's like, where's the thing I asked for?
I was just so excited I found something else.
Yeah. I'm like, yeah, but you're not finished yet. Only halfway there.
Yeah, that's why I never calculate things I don't need to. So no, I don't confuse myself that way. So
I need help with the geometry.
good. So your
Honestly.
triangle
So
looks
just
like
that first triangle.
Yeah. So your triangle looks like this, right? So you know this angle here. This is your 25.9. You know this distance here. That's your 2, and you're looking for this distance here. That's going to be your D1, right? So according to that angle here, this is the opposite side. This is the adjacent side. Keep rotating my hand like that, but yeah. So you know this angle. You're looking for this side here. You know this is the adjacent. This is the opposite. So tangent is opposite divided by adjacent. So you should have D1 divided by 2 is equal to tangent of 25.9. So now find D1.
Gotcha.
And go from there.
I got 0.49.
Oh, I see what you mean. Okay. Start again.
Oh, but I didn't actually.
Because you need to add those
times
distances together then.
Correct. Yeah. So that's only the distance from the first triangle.
I just started with the second one first.
Oh, there you go. That's fine.
Did you get 0.97 for D1?
You talking? Are you asking me or to Katie?
I don't know.
Yeah, I got 0.970725 for D1. Yeah.
Oh, wait.
Yeah. Okay. I'll be right back.
Okay, and we use.
All right. How we doing, ladies?
You gotta find.
We're working on the math for the second one.
Oh, okay. Good. Yeah, so that one you can just use all the equations that we wrote down in class since they're both converging lenses. So you don't have to go through all of that. That's fine.
For your distance of the object, then do you take 56 minus that 20.35 number?
Yeah, if that's the image distance you found, then yes. Yeah. So then the object distance 2 would be 56 minus that image distance 1. That's correct.
Okay.
Yeah. So So
I got 35.65 then for that.
let me check here. So what?
That's what I got too, Shannon.
Okay. Then, still using that equation, you would stick that back in there for your DO and then find your DI 2, I think.
Correct. That's right.
Okay.
36 minus 1. Yeah, so object distance 2 should be 15.65. Yeah. Oh, I used 36, not 56. Okay, that makes sense.
What'd you guys end up getting?
For the final image distance, I got 29.03.
I got
Yeah, I
20.02.
I just rounded it and kept it at 29 for V2.
Yeah, so it should be 29.0265. Yeah. So any one of those is fine. So, yeah.
So that's our final image distance, and then we have to find the magnification. So that's the M1 equals negative DI1 over DO1. So that'd be our 20.35 number, and then it'd be negative divided by 36, I think. Yeah, that's our object distance. Is that right?
Yeah, so it should be 0.46 should be your magnification.
That's for your first one.
All right. See you, Molly.
See ya.
She going back to work?
Yep. She said they're shorthanded. She has to go.
Gotcha.
I think we finished the first one. So I'm just pulling up the PowerPoint for the second one.
Good. Very nice.
Yay, okay, I got it.
Anytime I'm on Zoom, everything else on the internet just runs so slowly, though. It's painful.
Okay.
Yeah.
I'm gonna have to rewatch lecture today because my internet's just been so terrible.
Gotcha.
Live video just chews up a bunch of bandwidth. Need to get faster internet.
And mine does pretty well, actually, because you know, I'll be doing Zoom. My wife will be on her computer someplace else. My kids are watching, you know, YouTube and things on TV, and it seems to be fine. So apparently, I'm paying way too much money to have faster internet, but in this case, it actually works. So.
All right, let's see here.
Check on the others.
Gotta find our image distance, right? Where's the image location? Yeah, so
I did the 1 over 18.57 minus 1 over 22.5.
I think that's right. you have to take that to the,
Oh, the power -1.
one, yeah. I think that's right. Let me calculate that real quick. What did you end up getting?
1.06 meters.
Nice.
Carol, what did you say you got for the focal length?
For this one,
Yeah.
is it the 18.57 centimeters? I did all these last night since they were already posted.
I got 106.32. So then, will we have to change that to meters then?
That's what I did. That's how I got the 1.06.
Okay, so 1.06 would be our distance image. And then we define the size. So that'd be our HI for the image height. So that would equal negative DI over DO times the height of the object. Yeah, I think so. Is that what you got, Tara?
I think I noticed a mistake there because I stayed with the 106.3 versus keeping with the meters of 1.06. So I'm redoing that part now.
Okay.
So what was the question?
I'm probably gonna convert everything to meters, I think.
You don't have to, but you can if you want to.
Do you want that in centimeters then for that
Well,
size?
are you looking for the magnification?
The size.
Yeah. So no, it's as long as you keep the 106.3 is in centimeters. So that means the magnification is going to be the 106.3 divided by 22.5. So if you do that, then that's dimensionless. And then the size, as long as you take that and multiply by 3.75 millimeters, then your answer is going to be in millimeters.
Okay.
So you don't have to convert it if you don't want to. As long as you're dividing those two numbers in the same units, then
Okay.
that's fine. So,
I
yeah,
see.
so the final size should be about 17.72 millimeters.
And it's negative, right?
Correct. That's right.
Okay.
Yeah, so the negative in this case means it's inverted. That's right.
And then the positive value for the image distance means it's real.
Correct. That's right.
Okay.
Exactly. Good job, Tara. That's right.
Thanks.
And then it's inverted, right?
Correct. Yeah, because the height is negative, so that means it's inverted. That's right.
First one's upright and then inverted and upright. Okay.
Mhm.
What is the position of the final image? Okay.
We're going on the second one or the third one?
We're working on the second one.
Second one. Okay.
Yeah.
Just got done drawing the
All right,
ray
so-
diagram.
Okay. Got it.
I was telling her mine are terrible because you'll draw one and you're like, so based on the diagram, it should be past the focal point and the magnification should be smaller. And I'm like, my drawing shows it on the focal point and it's about the same size, but okay. I'm just terrible at drawing straight lines.
True. True. Yeah.
So if anything, it's taught me not to completely trust my diagram.
Yeah, that's true. Yeah, when I teach the engineers in the 206 version of this class, they all have rulers with them all the time, so they're drawing it all beautifully and precisely. And
Yeah. Minimize the mistakes, which I guess if you're an engineering major, that makes a lot of sense.
Yep. Yeah. They love it when they can break out their rulers and things. So.
There you go.
Yeah.
Doing the math for the final image distance now.
Okay.
So everyone's all set?
Yeah, I think we're done.
Very good. All right. So, yeah. So Jolie, I already talked to you, so you're good to go. Shaylin, I'll talk to you in a minute.
Okay.
So Julie, Tara, did you want to ask me any questions or anything before we go? Or-
Can I email you for an updated grade?
Sure. Yeah, that'd be great.
All right. Thank you.
You're welcome.
Bye, guys.
Bye.
So Shaylin, if you're just here, I'm going to go ahead and stop recording so that way I don't post this all over the internet. So, all right. So let me